Hi, how are you all doing today? We'll get started in just a minute. We'll just wait for a few more people to join us, and then we'll make a start on our workshop today. Okay, hi, how are you all doing today? I'm Adam Taylor, and today we're going to have a workshop which we're going to create for the Basys3 board. We're going to create a breakout game for that, and we're going to do this over 2 sessions. So if you've never seen Breakout before, I have a quick video, hopefully, that you will all be able to see as to what we're going to be doing. So this is what we're going to be creating at the end of the day. It's a nice little game that moves about and is running on the Basys3 board. So it should be a good fun application to create, and it will be a great learning experience for us as well, because we're going to go through several techniques. You know, we're going to put a MicroBlaze processor in there. We're going to use some high-level synthesis. We're going to use some RTL. We're going to use some IP integrator, and it's going to be a real lot of fun. We've got a couple of people today from Xilinx with us. We have Megan and Brittany with us from Xilinx. They're going to be monitoring the chat. So if you've got any questions or anything that I've missed that you want further explaining, please put it in there. We also have put links into the material to enable you to get started and to download it from my GitHub account if you've not already had a chance. All we need today for this is the material that's on the GitHub and Vivado. I'm going to be using Vivado 2020.2, but it's going to most versions of Vivado will be fine, along with a Basys board. So our objective for today is to build the actual bit stream. So build the bit stream that we're then going to use in the next session when we create the software application that's running in Vitus. So today we're going to be building this hardware application. So to do that, I'm going to be using Vivado. So I'm going to switch my screen over now. So hopefully you can see my screen, which is showing Vivado running. And we're going to take a step through, and we're going to run through this. So if you've been to the GitHub just one last time, you can download the step-by-step instructions, and that's what we'll be following them through today. The first step we're going to make actually is to make sure that we've got the correct board installed to be able to target the Basys3. So the first thing we're going to do once we've got Vivado open is we're going to go to the Xhub stores. We're going to click on it and we're going to open it. And now, if you've not opened this before, I actually uninstalled the board earlier on just so as I could demonstrate this. But we have the Xhub store. So when that opens, we're going to click on boards. We're going to find the Digilent part in there, and we're going to scroll down until we see the Basys3. Now, if you don't have a green little check mark next to it, what we need to do is we just need to right-click on it and click install. And this will go away, and it will get the board from the Xilinx board store, such that we can start using it within Vivado. Now we've got that board, we can actually begin to create our project. So what we're going to do is we're going to click on Close, and then we're going to click on Create Project. I nearly went to Open Project, but we're going to click on Create Project. Once we've done that, we're going to click a location to a project that we want to a location that we want to store it in. So I'm going to call this one here, and I'm going to call this one Basys Live, because that's what we're doing today. So I'm going to click on Next to create the next project. We're going to create a register transfer level project, an RTL project, but we're not actually going to specify any sources at this time. We're going to pull those in a little while. So can you just make sure you've got this option here ticked, which is do not specify sources at this time, and then click on the next button. Now here's why we needed to define the parts that we had installed on our device. So we're going to go to boards, a little slow. We're going to go to the drop-down menu here. We're going to select Digilent Inc. And in this case, the Basys3 is the only board I have to target. What you can do is, once we've done that, is we're going to follow on and click on Next. Then we're going to click on Finish, and this will give us a project that's going to got everything we need to target the Basys3 board. So hopefully, once we've got this Basys3 board up and running, we'll be able to, we can create a project and we can start working with it. So if you've never seen Vivado before, what you'll see here is the project summary. And when we've done our compilation and our implementation, we'll be able to see everything here. Once we can see all the sources that we're going to add into our design here, and then we have the flow manager down here where we're going to control the flow of our design and show that design. Once we've done this, the first thing we're going to do is we're going to actually create a block diagram. So we're going to create a very visual design of our FPGA today. We're going to pretty much like using chunks of IP blocks to connect it all together. So we're going to click on create block design under the project manager flow navigator. We're going to come over here and we're going to click on create block design. Now, once we've got the block design created, what we're going to do is we're going to, the option to create the block design, what we're going to do is we're going to click on OK, and we're going to leave the names and everything as it is, such that we can use it. Now, it'll take a few seconds to run through, and my machine always seems to run a little slower when I'm doing a webinar. But hopefully, but once we've done that, you'll see several things appear. You'll see we get this nice diagram here that we can create our design on. And we also have the actions here, so we can see the sources, the designs, the signals in our design. Importantly, though, we get this new tab called board, and this contains all of the information about the board. So it's board aware for the basis board. So it will actually show you it can help us pull through various elements if we want to try interfacing with them. So if we want to interface interfacing with the push buttons or the 7-segment display, as we're going to do, we can use these elements. So as we're looking through it, the first thing we're going to do actually is we're going to drag and drop some elements across onto the block diagram. So the first thing we're going to do is we're going to grab this here, the system clock. And what we're going to do is we're going to pull this all the way across onto this block diagram. After a few seconds, we'll see that we get a nice warning saying we've created a block diagram. And then we're going to click OK, OK on that. What we're also going to do is we're going to pull across the reset signal to give us a reset for this clock. So what we're going to do is we're going to grab this reset signal down from the boards menu here, and we're going to drag that across, and you're going to see how it automatically jumps to the reset signal. So then we're going to click OK, and we've connected the reset. So we've now got a clock and a reset connected into our board, and a clock wizard that's going to give us the ability to create the different clock frequencies that we want to use in our design. What we're going to do then is we're going to double click on this clock wizard such that we can re-customize it and change the number of clocks that we've got coming out of it. So we're going to click on the clocking options, and we're going to enable clock 2 and clock 3. And clock 1 we're going to set to the high speed of 20 megahertz. So we're going to set that to 20 megahertz. We're going to set clock 2 to 25 megahertz. This is really high speed logic design here. And we're going to set clock 3 to 50 megahertz. And once we've done that, so you'll see actually that the requested frequencies as well become there. So sometimes if you ask for a slightly different frequency, we can't get the video as we're going through that. We can't quite get the exact frequency, but using this we can. So that works a lot better with that. So once we see all this running through, we can click on OK. And as we've got that, now we've got that block diagram in there. The next thing we're going to do is actually we're going to add in a processor core. So we're going to put in a soft core processor, and we're going to use that for a lot of our applications and run through this. So what we're going to do then is we're going to click on this plus button here, And in this box here, we're going to type in MicroBlaze, or we're going to type in MicroBlaze, and you'll see that we can bring in a MicroBlaze. You see the MicroBlaze system here. So we'll double click on that. And then we'll just zoom out a little bit. So now you can see that we have not only a clocking wizard, but we also have a processor system in our device. Of course, so far, actually for the processor system, what we've not done yet is we've not actually configured this and got this configured for our application and for our system. So what we're going to do is we're going to do that in the next lab. So what we're going to do is we're going to click on this one. Vivado is really helpful. It wants to help us make a solution. So what we're going to do is we're going to click on this option here called Run Block Automation. Now this is going to go away and going to do some generation for us once we've configured the design exactly as we want it. So we're going to leave the preset at none. But the local memory is where our software application is going to run from. And actually, we're going to have a fairly large software application. So we're going to set this to have 128 kilobytes of on-chip memory. We're going to leave everything else unconfigured. So we're not going to have any ECC. We're not going to have any cache. We're going to want a debug module. And we definitely want the AXI port enabled because we're going to be connecting things to it as we move down. And then finally, we're going to have a clock connection. And we're going to run this MicroBlaze not very fast. We're going to run it at 20 megahertz. And this will help us achieve our time enclosure. Now, once we've done this, we're going to click OK. And we're going to wait a second or two. And you're going to see it's going to run through and it's going to recreate the system around our device such that we can start doing it more. So now we've got a fully functional MicroBlaze system in our processor in our design. It's got external block memory it can run from. It's got the clocks connected to it can run from. It's got a debugger connected such that we can debug it in Vitus when we do the next session in Vitus. And it's got a reset system such that when we've powered on the board, the reset system will bring the the board up. The next thing we want to do is to bring in a AXI UART. So again, what we're going to do, because at the moment we've got this nice little processor, but we couldn't even say hello world if we wanted to. So what we're going to do now is we're going to use the USB UART that's available on the Basys board, and we're going to connect that in. So we're going to find this on the board. We're going to grab the USB UART and drag it across onto the block. And we're also going to do the same with the 4 push-button switches. I'm going to drag that across and put that on there as well. So this is going to allow us to talk to the 4 push-button switches and to the USB UART that we have on the Basys board. The next step, though, is we're going to double-click on the GPIO block here to re-customize it, and we're going to actually turn it to. We're actually going to enable its second channel. We're going to make all the second channel all outputs, and we're going to set this to 16, a width of 16. And we're going to use this as part of our control system for controlling some of the logic that we go as we go further on. So we're going to click OK on that. And I apologize. I realize this is going at quite a fast rate, but we will be recording it and it will be available for you to watch later on. If you've got any questions or anything, please feel free to put it in the chat. If you're having some video issues with it as well, I saw a few messages with that. I think there is an issue with some browser. I think Chrome might have some issues with it, but I'm not sure. But there is a quick Google might help you there as well to help solve that. So once we've got both of these, this installed and created and in, what we're going to do. Oh, that's good. I'm glad Chrome's working well. What we're going to do is we're going to add in some custom IP. So if you clone the repository that I made available earlier on from the GitHub, you'll find there's a number of IP blocks in there. And the first one that we've got in there is we've got a register transfer level file in there, and that's going to drive the 7-segment LEDs. We have a constraints file that's going to control a little bit of the I/O for us that's not controlled by the definition on the board file. And we've actually got a high-level synthesis block that we're going to pop in there. Now, that high-level synthesis block's actually being written in C and synthesized into RTL, and we'll take a look at that in the next lab. But that's actually the element of the design that's going to be doing a lot of the drawing on the window. When you see it, when you output this externally, it will be this HLS block that's running through a lot of the drawing. What the MicroBlaze is going to be doing is calculating the positions of the ball, the positions of the bat, and updating this HLS block as to where that data is. So if we have this, so if you've cloned this, and hopefully I cloned it early on, we can go back to our sources. We can go to the add sources option here, and we can see that we've got the option to add or create design sources. So this is what we're going to do. We're going to click on next on this one, and then we're going to click on add files, and we're going to navigate to where you've downloaded your application, where you cloned the directory. So for me, it was just sort of one level down from where my project is working. And then we're going to add in the 7segment.vhd file. This is just a simple file that will take a number and will pull it through and help you display it on that 7-segment display that is available on the Basys board. So we're going to click OK on that. We're going to copy the sources into the project. We don't have to do this, but it makes it a little bit easier to do. And then we will click finish on that, and that should bring the design in. I've just realized actually on the slide that is next, slide 23, actually is slightly in the wrong position. So we'll come to that in a moment. We should actually be looking at slide 24. So under our design sources now, we should have this 7. Oh, sorry. It's not in the wrong position. It is in the right position because we want to add the 7-segment display onto the top of the design, and we can't do that when it thinks it's the top level design. So what we're going to do is we're going to select this design one here, the block diagram. We're going to right click on it, and we're going to ask Vivado to create us a VHDL block diagram. So we're going to click on create HDL wrapper. We're going to let Vivado manage it because we're really not interested in rewriting this netlist every time we make a change. So we'll let Vivado manage it. And it fails due to clocking because it's, hang on 1 second. Let's just connect these two clocks together. And then we'll try that again. Let Vivado do it. There we go. And what we can do then is we can right click on here and we can set the wrapper as the top level of our HDL file. And that's important because what we really want to do is we want to take this 7-segment LED file that we've just loaded into the design, and we want to pull it across onto the block diagram such that it connects onto our design. Once we've got that, we're going to pull that across a little bit there. In fact, I'm just going to pop this window out so as we can perhaps see it a little bit better as I work on it at a higher level. So once we've got this, what we want to do is we want to connect the output from the GPIO here, the one on output 2 that we've just created, and we want to connect it to the input, so to the 15 input, and that's going to mean that when we write a number into this GPIO, into the second channel of this GPIO, what's going to happen is the number is going to appear on the screen, and that's going to appear on the 7-segment LED. Where are we in terms of clocking? Okay, and again, the clock, we want to connect the clock to the 20 megahertz, clock that we have there as well. I just saw somebody in the comments just say that the slides, that they don't have the slides. So if you got the slides from Crowd Supply in an email, they're telling you for a completely different session, not this one. So this is different to the notebook that was perhaps provided by Crowd Supply. So you have to go to get the instructions for this lab. You have to go to the GitHub that's provided at the top and download it, download and clone that directory and pull it down from there. Okay, once we've done that, what we're going to do is we're going to right-click on these two, and we're going to make the first one, and we're going to select Make External. And then on the second one here, we're going to right-click it, and we're going to select Make External again. Now, just because I have a slight difference in the namings, and I've set up all the XDC, the constraints files, we need to change the names of these two signals that have just been created to match the XDC file for each. So I'm just going to dock this back in a second, just so as you can see what I'm going to do. And then I'm going to click on the 7-segment one here, and over in the external port properties, I'm going to select this one, and I'm going to change its name to 7_seg. And I'm going to select this one as well, and I'm going to double click on that. I'll click on this one actually there, and I'm going to change this one's names to 7seg LED_AN. So we've got there to drive the 7-segment anodes and the and cathodes. Once we've done that, no, you're right. Somebody spotted my error there. It shouldn't have been connected to that. It should have been connected to the clock lines. It was a simple mismatch I made, John, when I was just trying to get the top level block diagram, the top level VHDL created, such that I could make that the top level and import this 7-segment LED. Once we've done that, once we've done this, I'm going to run the connection automation just so as we can connect in the GPIO and the AXI into our AXI network. That'll take a second or two to run through. And then back in the block diagram, you'll see now that the UR, and the GPIO, that they're connected into this AXI network. And this AXI network is connected to the MicroBlaze. So now we've got a processing system that's connected to the GPIO, to the push buttons. It can drive the 7-segment element, and it can also send out messages over the UARTs. So while we do this, I'll just pause for a second while everybody if anybody's following along, if they catch up. I'll take a quick scroll through and see if there's any questions I can help with. But please, if you've got any questions or any comments, please put through and let me know. I saw somebody asking about if you could do this on the Snickerdoodle, and you can follow through and you can do all this on the Snickerdoodle. The one issue, obviously, with the Snickerdoodle is it doesn't natively, if you've just got the SOM, it doesn't natively have a video output port. You would need something like the Snickerdoodle Pi Smasher or something to be able to connect an output. And in that case, you'd be outputting over HDMI. But the concepts and the techniques and everything I'm showing here can be done and used across everything else that we're going to see. So now we've got this, what we want to do is we want to pull in, as I said, we're going to be using a high level, synthesis IP. Okay, one, where are they coming from? Ah, yes, that's a good question. So somebody was just asking a question about whether the clocks should be connected to the clock out or to the clock input, and that's actually a good point in that I've actually misconnected the clocks. So what I'm going to do is I'm going to just disconnect this clock. Select the pin and disconnect the pin. I'm going to select this one and disconnect this pin. And then we're going to select the ones on here and just disconnect these pins as well. Oh, I've selected the entire thing doing that. Select that one, disconnect pin, and that one. I think we can leave some of these, but I'll disconnect them all, and then we'll just reconnect them all to the. So they should all be connected to this 20 meg clock. So this is what we will connect them all to. Oddly enough, actually, it would have been just to give it all. It would have been okay because the slave clocks, the clock domain crossing would have kind of happened in the AXI peripheral block here, provided it sold them. But now everything is nicely all running, all connected on that nice and simple output clock. And actually, we need to make this one the output clock as well. So everything we've got there is running at the 20 meg clock that you can see now. Yeah. Live projects, right? So we've got that. What we want to do is we want to add in our HLS IP core into the design, and this is what we've created now is a MicroBlaze processing system. So if we wanted to run Hello World, we could run Hello World. If we wanted to read the state of the buttons, we could read the state of the buttons. But as of yet, we've not got anything that's going to give us that video output path, that output thing, or draw the game as we were showing. So what we're going to do is we're going to add in a new repository. So to do this, we're in the project manager view. We're going to go to tools. Where's it gone? We're going to go to the IP catalog. Once we've got the IP catalog, you can see that we've got the Vivado repository. But actually what we need to do is we need to instantiate our own IP repository at this point in time. So we're going to right click on here and we're going to say add repository. And it's going to give us a location that we want to add a repository in there. So I'm just going to do this. I'm going to create a new directory under there and call it IP repo. Hopefully I can actually, no, I'm going to put it under that one. And I'm going to call it IP repo. So you'll see I've just created a new directory that this is going to be the location for the IP repo. And you'll see as well, once we've added that, we don't get any IP added to it. So someone in the comments was just saying they can't see the PDF files. They should be available under the lab one. So if you go to the, I'll just put this up on my screen. If you go to the crowd supply area, you go to lab one, you should see lab1.pdf, which gives you the instructions. Where's that gone then? Okay, so if you do that, you should be able to find those there. However, as we've got nothing in the IP repo here, we've got no IP in it, we've not actually added any into it yet. So what we want to do is we want to get that and add the HLS IP block in. So what we're going to do is we're going to click on OK. And then we're going to select this user IP repo that we've just created. And then we're going to go to add IP to repository. I'm going to click on that. And then it's going to open that in the IP repo, where the location where we stored our IP repo. So if we go up and if we navigate to where we downloaded, if we navigated and worked out where we downloaded where we cloned the directory from Crowd Supply, what you'll see is this this zip file, which contains the implementation of the high-level synthesis design. So if we click on OK there, we'll see that come down, and then underneath the directory structure, what you should see is not only now do we have a IP under there, but we also have this HUD available under the IP repo. And from that, we can start working with it, and we can start using it in our designs. So this module, the HUD module that we're adding in, is actually what's going to draw. So if you remember back to the video I showed at the start of the project, just to answer a question from somebody in the chat, if you go back to the video I showed at the start of this as to where we're working from, so this HLS module is actually the module that's going to draw all the positions. So it's going to draw the ball, and it's going to draw the bat, and it's going to do all the movement. It's going to do all the movement in real time, in live real time, as we're doing it. And in the next session, we'll probably get time to take a look at that HLS code, that C code, and show you what's in there. But it's much easier to write code in C and use HLS to get that implementation than it is to run that. So your system clock, so somebody was just asking, system clock is connected with a clock wizard clock 1. Is that okay? So the system clock should come in, and it should run into the system clock 1. And it should go through, and it should create everything else. Just have a locked one go. So that should give us a nice solution. I think actually that reset tree might cause us a issue there, because that's on the wrong reset. So I'm just going to disconnect that pin, and then it should be connected to that network there. Because we've got everything to just make it all synchronous to the right clock. But yeah, you should see that system clocking going on. Sorry, John, you need to have this up, Vivado up, and the instructions up. I realize it's a challenge, but the video will be available, so as you can look through it, and you can also ask lots of questions. You've got my email, so any questions you get stuck, just email me. It's much more fun doing it live than it is doing it sort of, you practice several times and it all works okay, and then you do it live and you connect the clocks up wrong. So now we've got our HLS. What we're going to do is we're going to start working through and adding in the video pipeline, essentially. This is the pipeline that's going to get us to be able to talk to the VGA that's displayed on the screen. So we're going to click on that plus button again, and we're going to add in the HUD button. So we're going to type in HUD, and hopefully we should see it there so we can see our HUD. So we're going to double click on that, and that will bring in the HUD. We're also going to add in a couple of other IP from the Vivado library. So from the Vivado IP library, we're going to add in the test pattern generator. And we're going to add in the mixer. Wrong. You're going to add in the mixer. So we're going to take in the mixer. So we've got these 3 now. That's jumped in. So we've got these four elements, essentially: the test pattern generator, the head up, the HLS one that we've generated, and the video mixer. Bruce will not need 4. You'll only, by the end of this, hopefully you'll only need 2 by the time we're getting to the second session. But it'll all be good fun as we go for it. What we're going to do is we're going to double click on this mixer block. So this mixer block is going to allow us to layer levels of video on top of each other. So what we're going to do is we're going to have the video test pattern generator, and that's going to be able to create colorful backgrounds for us. And we can change that however we want. We're going to have the HUD that's going to control the bats and the balls. And we're going to have the video mixer that's going to layer all this together onto the same video for us, such that we can layer the videos together. But we do need to configure this correctly. So if we double click on this, yes, the HUD IP is the one that was added from the IP repo. That's a badly named heads-up display. It's really an overlay generation, but that was the name I selected to do it. So we need to set this correctly. So, and the size of some of these configurations and setting options that we do on here will give us a larger implementation in the logic, and we've got a fairly limited logic. So what we're going to do is we're going to set the top for RGB. We only want 1 sample per clock. We actually only want 1 overlay layer. So this is going to give us the main input, and it's going to give us 1 overlay layer. And then we're going to change the maximum size, because we're never going to be dealing with like a full HD screen in the RTX. So we're going to set this to 800. And we're going to set this to 800. So we can really display an 800 by 800 IP, an 800 by 800 frame as we're working through this. And on layer 1, importantly, on layer 1, we're going to set this to be RGBA. So we're going to find from this list, we're going to find RGBA, which will be in here somewhere. RGBA. Yes, that's the one, RGB. So one of these was done on RGBA. So that's going to give us an alpha channel. So we've got Carlos, we're not really going to use the square resolution. It's just a little bit of just a little bit, just in case anybody gets it wrong. In reality, we're going to be generating an image that's a lot lower than the 800 by 600. We're going to go with, for the final one, we're going to go with 640 by 480, I think, is going to be the final what we program in software. Just being an engineer, I just wanted to add some wiggle room, shall we say, just in case people wanted to explore and experiment. So this is going to give us 8 bits red, 8 bits green, 8 bits blue, and 8 bits alpha. And that alpha bit is what's going to determine the opacity of the pixel as to whether it overrides the background image or not. So, and we're going to change this to be a streaming type, and then we're going to select RGB. So yes, we select RGBA and streaming type there, and we click on OK. You'll see we've then got a AXI control port. So this is a slow speed. I don't know why I'm touching my monitor. We have an AXI slow speed control port, and this is how we're going to configure it over software. We have an AXI video stream input and a AXI video 1. And these are the inputs that we're going to use to do our video. And we'd better get this the right way round, otherwise we're going to end up with overlays. So somebody was asking what's the impact if you keep them at the maximum. So it will just use more logic resources, because obviously it's got to be able to handle that, to have the resources in the logic to do that. So it'll use more logic. We're then going to double click on the test pattern generator, and we're going to change this again we don't really need a 4K one, so I'm just going to say we might want up to 800 by 800. And I'm going to leave all the zoom bars and everything, but I'm going to turn off the foreground. I'm going to turn off the foreground pattern as well, just to give me a little bit more saving. And I'm going to click OK on there. Now, what I should say actually is, if you've cloned this repo, there's already a solution. There's already a solution in there, a compiled project in there, and bit streams and XSAs and everything in there anyway. But as you bring this down, what we're going to do now is we're going to begin to connect this together. So I'm just going to move this HUD down a little bit. And I'm going to take the video out from the video test pattern generator. And I'm going to connect it to video in 0. Because that's the base video upon which we're going to add on the various layers. Once we've done that, we're going to take the HUD output and we're going to connect that to the video 1 there. And then we're going to run the connection automation. We're not going to worry about the external reset in on that one there, but we're going to click on the AXI, the HUD generation, the slave control, and the TPG control. And we're going to change the clock sources such that it is the 50 megahertz clock. Because we want to be able to, this is our image processing line. So we want to be able to process data in this pipeline much faster than we would if we were doing it other ways. So the pixel rate, actually, so this is a good one. So someone's just asking, how do we select the clock rates to use? So the clock rate for the output is actually the 25 megahertz. Is actually the 25 megahertz free clock that we did, and that's what's needed for a 640 by 480 output. The clock for the 50 megahertz for the image processing chain is because I want that to be running slightly faster than the output clock, than the pixel clock, such that we can buffer those in a as yet to be instantiated IP. And using twice the clock frequency in this case, because it's relatively slow, gives us a nice approach to doing that. So we're going to click on OK for that, and that's going to run through. And we should see then that we've got the if I click on maximize my design, we should see then that we've got this third clock that's connected to this, and these are all connected and running at 50 megahertz. The stream's going to be running at 50 megahertz. The slaves are running at 50 megahertz. So everything's nicely, all nicely done there in our design. And you can see the AXI peripheral as well down here. That's actually pulled it through and is running at, and has got everything all connected. So it will do all the clock domain crossing, and everything that we're going to do will be included as part of that. So I'm just going to regenerate my layout a little bit, just so as we can see it a little bit better. And what you'll see now then, now we've got this, is what we've got is we're not doing too bad for time. I was a bit worried about this. What we've got is we've got a MicroBlaze system as our starting point. We have obviously we have the UART to give us a hello world, and that's going to be one of the first things we check in the next session. We have the GPIO to control the 4 buttons, and we're going to use those 4 buttons to control our design. So we're going to use those 4 buttons to move the paddle left and right. But actually the up and down buttons, they're actually going to change the width of the paddle, so as you can cheat and make it harder or easier. What we've done then is we've put this HUD in, this head-up display. So this is this module really is the module that draws where the ball is and draws the bat. So it draws the size of the bat and the position of the bat on the screen and where the ball is on the screen. The MicroBlaze is going to be keeping track of where the ball should be according to its algorithms, and where the bat is from where you've moved it. But the MicroBlaze is going to be telling this heads-up display where to draw the ball, where to draw the bat on every frame. So it's going to every frame it's going to draw it into place. The test pattern generator, that's going to give us the background. So we've got a nice background, and we can have in the example video I showed, I've got the color bars, but you could have a red background, black, white, green. You could have a different pattern background if you wanted to, just to make it a little bit more interesting. And then we've got this AXI video. We've got this video mixer here that's gonna mix the 2 video layers together and put the heads-up display on top of the test pattern generator, such that you can see the ball and the bat as it moves about. What we need to do now, though, is we need an output path we need to be able to display on the VGA output signal. We need to display on the VGA outputs. And the VGA output on the Basys board is actually, it's quite straightforward. It uses a simple resistor divider to create the color. So we're just going to use the 4 colors. We're going to be using like a 4-bit resolution really at the end of the day for this, for each color. So 4 red, 4 green, 4 blue. But first, what we need is we've got this AXI stream interface, and the datas represent the videos coming through as an AXI stream, which is pretty much just a continuous stream of data. And we need to be able to convert that into a timing signals that a TV can use to know when to start a line, when to end a line, when to start a frame, when to end a frame. And to do this, we're going to add in a couple of additional blocks to help us generate all that timing and work. So the first thing we're going to add in is the video timing block. So we're going to add in the video timing controller, and we're going to add in a constant. Can't type today. A constant block. Now, what we're going to do is we're going to double click on the video timing controller to re-customize it again. And we really want this to just be generating the timing waveforms for our video. We don't want it to be detecting the timing, because that's not what we don't have a video input. We're just doing a video output. So we're going to disable the detection, and we're going to leave the enable. We're going to leave the enable going. And we're not going to make any other changes to that. And we're going to click OK on that. And then we're going to run the connection automation again. We're going to select the control here. We can leave the auto, but I'm going to select the 20 megahertz clock and run that. And there you'll see that that's being connected and pulled through into our AXI control network. What we want to do then is we need to add in a AXI stream to video out. So this block here, and double click on it. So this is the block that's actually going to convert the AXI stream into a 2-dimensional array using the information from the timing controller that's given to it. So we're going to double click on the AXI stream block to re-customize it again. We're going to leave pretty much everything the same, apart from we're going to tell it it's got independent clocks, and that is that the AXI stream clock is a different clock frequency to the clock for the pixel clock for the clock output. Once we've done that, we'll see it re-customize and draw, and then we're going to go from here. We're going to connect the video timing out to the video timing in. Excuse me. We're also going to connect the we're going to connect the clock enable to these clock ends. Even though it says N and it's got a little circle on the end, it's a little bit of a bug in Vivado, because they're actually enables that need to be active high, not resets that need to be active low. So we're going to connect those two to that to give us that. We're going to connect the, where's my screen gone? We're going to connect the output video from here, from the video mixer. We're going to take that across, and we're going to connect that. Oh, I've picked up the interrupt pin. That's quite annoying. We're going to take that across to the video in, such that we can see that video in. And then we're going to connect the AXI stream clock here. So this A clock, we're going to connect this to video to 3. Because it's running at the 3 megahertz time. We're also going to connect the enable one with the enable. We're going to connect the enable to this one here, and we're going to connect the video out chip enable to the chip enable as well. Okay, VTC's clocks, that's all done. We're going to connect the VTG CE pin here. We're going to connect that back to the gen clock enable here. And this allows the video, what this allows, it allows the video controller to the video stream to output to be able to put back pressure on the timing controller and adjust it slightly. And we're going to connect the SOF starter frame output to the SOF state there as well. And then what are we going to do? Once we've got all that done, we're going to connect the clock here. So so far we've not used clock 2. So we're going to connect clock 2 here to the clock here. So this is the 25 meg clock. So this is the pixel clock. So we're going to connect that to the video timing controller, such that the video timing controller generates a timing at the right pixel frequency. And then we're going to connect the output clock here also to that clock there, such that we have the right data. Let's just click on regenerate, just so as we can see it make a little bit more, begin to hopefully make a little bit more sense to us now as to what's going off. We need to connect some of the reset signals. Actually, we've not done that, so we need to connect the reset signal here, the AXI reset signal, to the that's a 50 meg clock, so we need to connect that one to there. And we need to add there's actually no need for that doesn't go anywhere. And we actually need to add in another, I could have just used the same reset one. How did that go? Could have sworn I added one in then. Clock 1, clock 2. There we go. Clock 3. We need a third clock reset just to work off our second clock here. We can add in the DCM locked to the locked and the external reset to the external reset. And then we can take the peripheral reset across to the video in reset there. Just redraw that again. So now hopefully everything should be coming together. And we now hopefully everything should be coming together. Somebody was just asking if this can be done in 2019.2, and yeah, there's no reason why it can't be done in 2019.2. And someone was asking if it can be done with the clock gen goes from the VTC. So the VTC, so VTG chip enable goes to the clock in enable there, and that just allows you to put some back pressure on the design. What we're going to do now is I'm just going to pop this back into the Vivado window for a second, and you'll see why in a minute. But I'm going to zoom in over in this area of the design, and I'll try and make it as big as possible. And I'm going to expand this output here, and then I'm going to click on certain things. So I'm going to click on the video horizontal sync, and I'm going to ask to make that external. And I'm going to click on it, and I'm going to, over here, I'm just going to rename that H sync. And we're going to do the same for the video sync, for the V sync down here. Make external. And we're going to do that there. We're going to do V sync. V sync. So we've got now the vertical and the horizontal sync, and this is going to tell the monitor that we're using how to draw it and where to draw it on the screen. And then finally, what we're going to do is we're going to add in 3 slice IP blocks, and this is because the output can only the output videos I was saying is only available to actually output 4 bits. Not the 8 bits that we want. So we're going to ask this to, we're going to use these slices. Just come over here, and then I'll zoom in a bit. We're going to use these slices to essentially prune off the video. So we've got a 24-bit pixel coming out. And what we need is essentially we need to pick off each color channel and pull it through. So we need to pull that color channel out. We need to find the correct color channel in the position, and then pull the four bits out from it. So this is what we're gonna do. So slice 0, we're gonna double click on, and we're gonna tell it that there's a 24-bit input, and we want it from bits 19 to 17. Sorry, I lied. It's not a 4-bit. It's not a 4-bit. It's a 3-bit resistor. It's a 3-bit resistor DAC. So we're going to tell that we want from 19 to 17. We're going to do the same for slice 1. We're going to again tell it it's 24, that we want 11 to 9. And for slice 3, it's 24, and we want 3 to 1. Okay, so this is going to give us the, this is going to prune us the bits that we want. And what we're going to do is we're just going to, we're going to make these outputs, make external. Make external. Make sure you're clicking on the pin, not the module. Make external. I'm going to save that. And then we're going to set slice. Let me get this the right way around. So slice 0, we're going to call VGA red. Slice 1, we're going to call VGA blue. And then slice 3, we're going to call VGA green. And this will give us all of the elements that we want to do. Okay, we've run through that one. Okay, that one. Okay, that one. So we should have. I'm going to pop this out now because we're getting nearly at the hour. Oh, it's a good job we said an hour-ish. I'm going to rerun the routine, reorganize it, and we can see now we have a nice. Oh, that's where that one went. You can see now we have a nice flow where we have the MicroBlaze processor, we have the interconnects, we have the video elements down here, we have the video creation elements here, we have the video timing element here, the GPIO, which is connected to the push buttons. We have all our outputs here. So we have our USB UART, the 7-segment display, and the slicers for the video. And everything there should be okay. So if I've drawn this correctly in the hour, we should be able to run the validation. If this validates with no errors, I'm going to be quite happy. So we've run that through, and hopefully you should see that in your design, that there are no errors or critical warnings in the design. And that's really good, because all we need to do now is, now we've got the design ready, we need to just add in the constraints for the outputs. Somebody said about a stream FIFO. We'll talk about that in a minute, because I didn't actually add a stream FIFO into the design, unless you're talking about under the timing module, the hysteresis. Oh, the FIFO depth here, and it just gets left as the default value of 1020 as 1024, and that's just the FIFO that it stores the pixels in before it tries to synchronize with the timing controller to give you the output. Now back on the sources tab, we're going to click on to add in the constraints. We're going to click on the add sources tab. Only this time, we're going to click on the add or create constraints. We're going to click on next, and this time we're going to click add files, and we're going to pull in the io.xdc that we created earlier on, that we pulled down earlier on from the GitHub. We're going to click OK on that. We're going to allow that to copy the constraints into the project. We're going to click on Finish. And then we'll see the constraints under our designs here with all the pins mapped through as we would expect. Now what we can do then is, all we have to do now, and this is why this project ends at this point in time, and when we've just about taken the hour, is save the design. And then we can click on this element here, which is, and I'm not going to run mine because it'll start using a lot of computer process, which will slow down the video stuff, I'm sure. But if I click on generate bitstream, I will get this launch runs come up, which will ask me to launch my runs. And then if you click on OK, I'm going to click on cancel for this. But that will then run you through the design, and it will take you through. And what you'll see up here is, when this is all completed, you'll see a bitstream, write bitstream completed tick here, and you'll be able to see in the downstream here in the project summary, you'll be able to see the utilization and the timing constraints. Now, we're going to leave the lab here for this session 1 at the hour, because hopefully if you've all followed along, you've got to that point. It's going to take a variable amount of time, depending upon your machines, to do this place and route and implementation, because we're going to use quite a bit. This is going to use quite a lot of the resources of the machine to do that. So it's going to take a little time to resources of the device to do. So it's going to take a little time to run through and give you all that time enclosure and everything, and pull it all together. What you'll see at the end of this is a completed bitstream, and in the next lab on the 1st of April. So if you've enjoyed this one, the next one will be a little slower because we don't have quite as much to fit in. But if you've enjoyed that one, then please register for if you've not already done so, please register for the one on the 1st of April. And we will run you through creating the software and getting you, we'll run you through 2 things. The first thing we're going to run you through is proving that the MicroBlaze actually works. The next thing after that is actually creating the application once we've seen that the MicroBlaze can say hello world. So this should run through and it should complete. If by the off chance it doesn't, or you don't get a chance to do it, or you don't have the board but you want to follow along, on the crowd supply workshop, you will see that I've made it up. You can't see because it's under there because it's raw, but you'll see that I've already made available to you the design1.xse, and that's the compiled output that you need from Vivado at this point in time. So if you can't compile it, if your process is taking too long, or you come across an unexpected bug in Vivado on a particular operating system implementation, everything you need to get started with Lab 2 is there. John, you were just saying, when will Lab 2 be pushed to Git? We've just reviewed the documentation now, the lab guide, so we'll be pushing it together. We'll be pushing it out in the next few days, hopefully. So I'm going to stop sharing my screen. I'm going to come back to the video, and I'm going to ask you before we end this session. First off, I'm going to thank you all for coming, and I hope it's been informative, and you've learned a lot. So somebody was just saying, what about the XDC? Aren't these data already configured in the Basis board files? And actually they're not, so not all of them are. So if you take a look in, let me just share my screen again. So if you take a look at my Vivado, if you take a look at the board definition here that's defined in the board output, we have the USB UART, the VSET, we have the PMOD connectors, we have the switches and LEDs, the 7-segment display, anodes and cathodes, and we've not connected to them. Because we're using a specific driver block that I've written. We're not using that, because if you pull that across, all it will pull across is GPIOs for you to write and control in software. And I've actually written an RTL block that makes it a lot easier. In essence, my RTL block, you just pass it the number you want to display, and it will display it. Whereas if you pull those two across, you would have to work that out for yourself. We're not doing anything with the QSPI memory in this one, so you don't need to do that. But you'll notice that the VGA is missing, and that's what we have under here. So we've mapped in the 7-segment display because we're using it in a different way, and we've mapped in the VGA connector as well. And then we've made a few changes to the VGA connector, to the VGA standard, so the drive strength and such like, because I had a rather large, it is, John, it's a shame it doesn't come out with the board files, but I had a rather large cable, and I noticed that if I was driving it too high with a too fast a current and too fast a drive strength, it was perhaps clipping occasionally on the VGA standard, and it was upsetting my monitor a little bit. Yeah, the US, and John makes a good point. You know, the USB PS2 port is not on there, is not on the list neither. But everything we've taught you today, you know, you can adapt if you want to work with the VGA or you want to work with the USB PS2 port. And maybe if people like this lab, we'll do, you know, and after we've done the game, we can perhaps consider in a month or so doing another different lab on the Basis or something with a different interface. So this is it. So if you click go, now you should have everything you need to get going, and come join us with that second part. Like I say, if you hit any issues, everything you need is available on the GitHub to come back and do the second part anyway. So we're not gonna leave you hanging and out there on your own. We've definitely provided that update, and I'll provide, as part of the third element, as part of the second lab, I'll provide you all the programming files and everything as well, the final programming files and everything as well. So someone was just asking if I show the generation of the platform interfaces in the next lab. Actually, no, because we're not doing any. We're just going to use the embedded flow for this. So we're going to be using the embedded Xilinx flow, not the accelerated flow, because it's an Artix device. It's not an MPSoC or a Zinc or an ACAP device. It's just a standard sort of normal FPGA. So that accelerated flow is not really suitable. So we'll just be going with the normal embedded development flow in Vitis. So in the next lab, we'll just be running through how to prove that we've not done something silly with the MicroBlaze, you know, and held something in reset when we should have held it in reset. But we'll be showing you how you can run that through. And then in the second half of the lab, we'll be looking at creating that application and writing that software. And if we get time, if it's not as rushed as today, or there's room available, or there's time available, or we run over a few minutes like we have done today, then what we'll do is we can take a look in the HLS code for this heads-up display block as well, if anybody wants to take a look at that. So finally, is there any questions, comments, or anything? Thank you to please put it in. I'm glad to see that somebody's generated the bitstream already. I was a bit worried because if I generated the bitstream on this when I generated it, I click go, and because I've got quite a powerful Linux machine running, it just literally hit 100% utilization of all the processors. So I didn't want to do that just in case it sort of dropped out and did this. But if you've got that bitstream, you're good and ready to go for the next one. And like I say, the 1st of April is the next one. It's April Fool's Day. Actually, I'd not thought about that, but that's April Fool's Day, so it'll be good fun. Any questions in the meantime? My email address is in the lab book that you've just downloaded, so please feel free to email me and reach out. And again, if you're interested and you like the stuff I'm doing and seeing, there's a lot more of this on my website at aduvioengineering.com, and people can see that as well. Particularly if you want to learn about other things such as Vitis acceleration and Zincs and MicroBlazes and such like. Right, I'm gonna leave it there. I feel like I've talked at you for hours, so thank you very much for coming. Michael say what should be on the table for next time. And that is basically you're going to need your Basys3 board if you've got one. You're going to need a USB cable to power it, and you're going to need an Ethernet cable and a monitor that does VGA as well. If you've got a monitor that does VGA, such that you can partake and play the game at the end of it. No Ethernet. We're not going to need Ethernet. I don't think there's Ethernet on the Basys3 board, is there? I actually don't have one to hand, and I'm kind of tethered to my monitor at the moment. But no, so there's no Ethernet. But everything's going to be done. We'll be debugging and building it over the JTAG debugger, just like you would any normal embedded software. So, right, I've been talking for far too long. I need to get a glass of water. So, thank you very much for coming, Megan, Brittany, Rebecca. Thank you very much for answering the questions as people have done. If you've written a question and it's kind of scrolled past and I didn't answer it, please don't think that I ignored it, because I probably just missed it. So please just pop it in an email and we'll take a shot from there. But anyway, I'm going to end this now. So thank you very much. And once this is out, if you keep an eye on my social media channels and my blog, we'll publish all the links to this such that you can see it and take it from there. Okay. Thank you very much. Have a good evening, good day, good afternoon, wherever you are in the world, and please stay safe in the pandemic. And I will see you all later. Thank you very much. Bye-bye.